In this question, we're going to deal with ethyl acetate. It's also known as ethyl ethanoate. It is a simple ester that is used as a solvent for glues. Two common ways to make ethyl acetate are a Fischer esterification reaction, where you've got ethanol and ethanoic acid making ethyl ethanoate, and then the alkylation of acetic acid by ethene. So they've got ethene and ethanoic acid to produce ethyl ethanoate. So the first question is to calculate the molar enthalpy of formation of ethyl ethanoate using the Fischer esterification reaction. So in this reaction, they've given us the reaction enthalpy. I can find this enthalpy of formation in the data booklet and this enthalpy of formation in the data booklet, so then I can calculate this. So essentially, my strategy for this is going to be to find the reaction enthalpy equals the sum of the number of moles times the formation enthalpy of the products minus the sum of the number of moles times the formation enthalpy of the reactants. And I know the enthalpy because it tells me here that it is an endothermic reaction because it has it as a term in the reactants, and that it's 316.9 kilojoules. So 316.9 kilojoules is going to be equal to the formation enthalpy of the products, which is the 1 mole times the formation enthalpy of ethyl ethanoate minus the reactants. And the reactants have 1 mole times the formation enthalpy of ethanol, which is negative 277.6 kilojoule per mole, plus 1 mole times the formation enthalpy of the ethanoic acid, which is negative 484.6 kilojoule per mole. And these values will be equal. So I can calculate the formation enthalpy of ethyl ethanoate by isolating it. So I'm going to just do a little algebra. I'm going to have this. So I have to take this side over to this side. And so it's going to be positive 316.9 kilojoules minus this value. And if you put those back together, it's negative 762.2 kilojoules. And so this comes out to positive 445.3 kilojoules. And so the formation enthalpy for ethyl ethanoate equals positive 445.3 kilojoules per the 1 mole, because there was 1 mole in the reaction, right? So we made 1 mole of it, so it's per 1 mole. The second question says to calculate the reaction enthalpy for the alkylation of acetic acid by ethene. And I'm going to, again, use Hess's law with formation enthalpy. I've got this in my data booklet, I've got this in my data booklet, and I've just calculated this. And so I can use that calculated term to get this reaction enthalpy. It's going to be equal to the sum of the number of moles times the formation enthalpy of the products minus the sum of the number of moles times the formation enthalpy of the reactants. And my enthalpy is going to be, now I've got 1 ethyl ethanoate, so it's 1 mole times the formation enthalpy of ethyl ethanoate, which we just calculated was positive 445.3 kilojoule per mole. That's my 1 product. And then I'm going to subtract the formation enthalpy of ethene, so 1 mole of ethene times the molar enthalpy of ethene, which is positive 52.4 kilojoule per mole. I've got that from my data booklet. And 1 mole times the formation enthalpy of ethanoic acid, which is negative 484.3 kilojoules per mole. I put that into my calculator, and the enthalpy of this reaction equals positive 877.2 kilojoules. So the formation, or the reaction enthalpy is this, and they didn't ask for the molar enthalpy, so I don't need to. So if I was going to put that into here, this will be equal to positive 877.2 kilojoules. Right? The next question says, if 200 grams of ethyl ethanoate is created by the Fischer esterification reaction method, what amount of temperature change would occur in a 4-liter beaker of water? Is the water bath cooled or heated by the reaction? Well, we can answer, is it cooled or heated by the reaction, as soon as we take a look at the reaction enthalpy. It's endothermic, so if it's endothermic, the reaction vessel is going to cool down because it's using the energy up. And what we're going to end up with is one of these situations where we've got N delta H equals MC delta T, and we're going to isolate for delta T. So delta T equals N delta H over MC. And the delta T is going to be cooling down, so it'll decrease the temperature of whatever the bath is by that amount. Now, the N is going to be equal to the mass over the molar mass. They told us it was 200 grams, and the molar mass of ethyl ethanoate is 88.12 gram per mole. And so we get 2.27 mole. We've already got the, so 2.27 mole. The molar enthalpy is positive 300 and positive 316.9 kilojoule per mole of the product being reacted, and we're going to take MC, so the mass is 4.00 kilograms because it's 4 liters, and the C is 4.19 joules per gram degrees Celsius. And so the temperature change in this reaction is going to be equal to 60.3 degrees Celsius. So it told us how much is being created, how much energy did it take, and so we've done that. And the last question says to sketch a reaction pathway diagram for the alkylation of acetic acid by ethene. And so it's endothermic as well. So the last reaction, or the last question, is asking us for an EP. It's an endothermic reaction, and so we've got the reactants. We've got ethene and ethanoic acid are going to absorb a bunch of energy, and we'll get some back to make our ethyl ethanoate. And the enthalpy of this reaction is positive 877.2 kilojoules. This will be like time or something like that, and that's alkylation of acetic acid by ethene, and we're talking about the enthalpy. So enthalpy of alkylation of acetic acid by ethene, something like that would be a title that would work. So that would be a kind of a reaction pathway. We have to put in more energy, but we get some of it back. And so the catalyzed reaction still has the same start, still has the same end, but now the activation energy is decreased. And so it's got a lower activation energy, and it should speed the reaction up. So we should have more successful collisions to create the product because it requires less energy to get to the product. So it says, sketch a second line for the catalyzed reaction pathway and comment on the effect of catalysis. So catalysts are not used up in the reaction. They are returned to the beginning conditions. but we get more successful collisions, so the reaction speed or the reaction rate is increased in the forward reaction.